Okay, the second talk is by Parveen Kumar from IIT Jammu, and it is on quantum state engineering by steering in the presence of errors.
Hi. Good afternoon, everyone. Let me start by thanking the organizer for having such a wonderful meeting and for giving me the opportunity to speak one of my work here. So I will be talking about quantum state engineering by steering in the presence of error. So this work is published under these two papers. So as we go along, I will explain what I mean by quantum steering and what I mean by errors. So let's get started. So what is quantum steering? So typically people use quantum steering as a measure of some non-local quantum correlation, but that's not what I'm talking about. I'm talking about a process that can take an arbitrary initial state. This initial state could be a pure state or could be a mixed state, and steers it to a desired target state. And again, the target state could be a pure state or it could be a mixed state. So we have a process that converts our initial state to a desired final state. And such kind of process like quantum steering, we also call it as a quantum state engineering protocol. We do have some typically used quantum state engineering protocol. One of them use projective measurements. So for example, if you have a spin half system, which is in some arbitrary state, and you want to prepare it to, let's say, spin up state. So the simplest thing to do is you measure the sigma z projectively. So half of the time it will collapse your superposition state into the up state. So then you have your target state. But in case it fails, in case it gives you the down state as a measurement outcome, you can always say that I can apply a unitary feedback and go to my target state. So this probabilistic measurement outcomes ensures that such kind of protocols does not have a guaranteed success. And if you use the feedback to rotate your post-measurement state to the desired target state, your feedback has to be very much fine-tuned. Like if it goes epsilon here and there, your fidelity drops. And then there are issues with the larger system. Like if you have a larger system, then the set of possible measurement outcomes are also very large. And depending on each measurement outcome, you have to design another feedback scheme to get back to the target state. And then come the questions of robustness. We all know that the experiment are always exposed to different noise. So if you have noise, then the robustness of such kind of state engineering protocols are very much under doubt. Then the second thing people do is thermalization. Like if you want to prepare a state in some ground state, so the thing to do is like you couple your system with a cold bath. So ultimately your system will relax down to the ground state. But if you have a larger system, then in order to prevent all the thermal excitations, your bath has to be really, really cold, which is a hard thing to achieve. So we propose a solution out of this problem. We propose a protocol, and there are a certain checklist for our protocol. The first checklist is we should have a guaranteed success, like our success probability should not depend on the measurement outcome. And we should not require any fine tuning. And we should be able to achieve any target state, whether it's a pure or mixed. And our protocol should carry at least a reasonable amount of robustness against all kind of errors. So we propose a protocol that use continuous quantum measurements, not the projective quantum measurements, but the continuous quantum measurements. Okay, so let's get started with the textbook definition of quantum measurement. What do I mean by quantum measurement? It's essentially, I have a system which is in some state. I connect it with the detector and then I measure the detector. So half of the time my system will collapse to the up state, or half of the time it will collapse to the down state. Of course, the measurement probability depends on the coefficients A and B. And this is what we call state collapse. Apart from the projective measurement, we do have a concept of weak measurement. So in the weak measurement, we couple the system with the detector very weakly. And because of the weak coupling, we can extract only a partial information out of the system state. So a classic naive example would be, what if we try to look through the door via a blurred mirror? So we can identify that there's a person standing outside, but we cannot really say whether the person is a male or female, or whether the person is looking towards us or it's looking away from us. So this is kind of weak measurement we do. Okay, so very schematically speaking, the measurement is a three-step process. In the first step, we couple the system with the detector using some Hamiltonian. So this coupling induces some entanglement between the system and the detector. And the next step, we measure the detector projectively. So because the system is entangled with the detector, so measuring the detector will tell you something about the system state. And since we have a two-level detector, so the post-measurement detector state could be up or down. If the state of the detector remains same, like we initialize the detector to an up state, and if after the measurement it goes to the up state, so we call it as a no-click measurement. And if the detector state is flipped after the measurement, we call it a click measurement. This is the terminology we use. Mathematically speaking, we have at a given time t, we have the state of the detector and we have the state of the system. So they are very much decoupled, so we write them in a composite state manner. And then we evolve the composite state using the interaction Hamiltonian. And the evolution follows the Schrodinger equation, so it's just the unitary evolution. In the next step, as I mentioned, you measure the detector state projectively. And depending on the post-measurement detector state, there is a different back action that acts on the system state. And these back action operators are called as a Krauss operators. And you can see here that the Krauss operator does depend on the interaction Hamiltonian, like it does depend on how you couple your system to the detector. And if you combine these two measurement outcomes, so we can write down our stochastic Schrodinger equations. So the first term in the stochastic Schrodinger equation, it comes from the no-click measurement. And the second term comes from this click measurement, and there's a stochastic parameter dn sitting here. So dn can have value either 0 or 1. If you get a no-click measurement, the dn is 0. If you get the click measurement, the dn is 1. It's really a Poissonian stochastic variable with the mean average given by the jump operator L. So the jump operator depends on the Krauss operator, and the Krauss operator depends on this interaction Hamiltonian. So essentially, if you want to have a clever measurement-induced evolution, so you have to be very careful in selecting your coupling Hamiltonian between the system and the detector. So you can talk about the average over different measurement results. You can say that, okay, I have a detector, but at the end of the measurement, I don't look at the detector. I just throw it away and pick out another detector from myself and then couple it with the system. So in that sense, I'm averaging over all possible measurement outcomes. And once you average over measurement outcomes, we get the mixed state. And that's why we have to talk about the density matrix. So the evolution of the density matrix is just m rho m dagger, and depending on different measurement outcomes. And if you go to the continuous time limit, if dt is very small, you can write down the Lindblad master equation. And here you see that the dissipator in the Lindblad master equation is essentially come from the measurement or what kind of jump operator you will have in your dissipative dynamics. It totally depends on what kind of Hamiltonian you use between the system and the detector. And the whole idea is to design this dissipator in a clever way so that the steady state of this evolution, so the steady state of this measurement induced dissipative evolution is your desired target state. So for an example, if choose your system detector interaction Hamiltonian in this particular form where J is the coupling and sigma x on the system Hilbert space and on the detector Hilbert space plus sigma y on the system Hilbert space and detector Hilbert space, then this kind of system detector interaction Hamiltonian will lead to these particular Krauss operators. And from the Krauss operators, you can see that they will steer your system to a specific target state. And I can write down the averaged, the blind measurement evolution, blind in the sense like I don't look at the measurement outcome. And from the continuous time limit, I have this particular Lindblad equation with this specific jump operator. So one can easily see from this jump operator that the steady state of this evolution is the up state. So no matter where you start from, this particular dissipative evolution will always take you to the up state. And gamma, which depends on J and dt in this particular manner, controls the measurement strength. So we denote this up state as the north pole of the Bloch sphere. So this is the ideal, simplest measurement-induced state preparation protocol. So here I have only a coupling Hamiltonian. I don't have any local Hamiltonian. In principle, one can have a local Hamiltonian. So what happens if I add a local Hamiltonian to this part? So the local Hamiltonian acts only on the system Hilbert space, so it will just appear as a additive term in the dissipative evolution. So I'm just talking about a single qubit state engineering protocol. So my local Hamiltonian could be anything. It can be an arbitrary 2x2 matrix. And theta and phi are the polar angles on the Bloch sphere. So depending on theta and phi, the steady state of this particular evolution forms a manifold, which is an ellipsoid. So you take a specific choice of, so now I have 4 parameters in my problem. One is the omega, which controls the strength of the local Hamiltonian. Another are the theta and phi, which controls the direction of the local Hamiltonian, and the parameter j, which controls the measurement strength. So if you choose a particular combination of these 4 parameters, you go to a particular unique steady state on this ellipsoid. Yeah. That's one way to do. Another way to do is after every time step, you reset your detector. So you have a single detector and you evolve your detector with the system for time step dt. And at after this dt, you just reset your detector to the original state. Or the another way is just to decouple your detector and attach a fresh one. Okay. So we see that if we want to go to a specific target state, we have to just tune our parameters. So, and this target state could be mixed, like you see that only the North Pole touches this ellipsoid, all other states on the ellipsoid are the mixed state. You can rotate this ellipsoid by rotating the overall setting. That's one way to do. Another way to do is you can choose to measure in different bases. For example, if you measure in the z basis of your detector, you get this blue ellipsoid which is pointing towards the z direction. You can decide to measure in the y direction or x direction. Accordingly, you will get ellipsoid that points towards y direction or to the x direction. So by rotating this ellipsoid, essentially you can cover the whole interior as well as the surface of the Bloch sphere. So this essentially means you can target any arbitrary pure or mixed single qubit state using this simplest protocol. Other thing to notice here is that although a unique choice of all these 4 parameters takes you to the unique state on the ellipsoid, but vice versa is actually not true. So for example, you see the red dot here is a particular mixed state and it lies on all 3 of these ellipsoid. So this means there are at least 3 protocols, 3 choice of these parameters which can take you to this red state. So out of these 3 possible sets, which set I should use in my state preparation protocol, it depends on which one is more optimized set. And what do I mean by the optimization? I mean I want to reach to my target state in the least possible time so that I can prevent all kind of experimental imperfections. So in that sense, I can optimize my state engineering protocols in the sense that I go to my target state as quickly as possible. So I can do this optimization, and here I plot the optimal decay rate versus purity. Why purity is a good parameter here? Because we know that the two states with the same purity are connected by the unitary evolution, and essentially these decay rates are the eigenvalues of the total evolution operator. So total evolution operator here is the Lindbladian. It's a 4x4 Lindbladian, and Lindbladian have one of the eigenvalues will be 0 because we have a steady state in our solution. Other 3 eigenvalues will have some real part and some imaginary part, and the real part essentially controls the decay rate. So what really we want to do, we want to maximize the smallest decay rate. So that's what it is. So we see that this pattern can be divided into 3 regimes. One is the low purity regime, one is the mid purity regime, and one is the high purity regime. So in the low purity regime, if you increase the purity, your optimal decay rate also increases in a particular fashion. And then comes the mid purity regime, where the optimal decay rate is essentially a plateau. And then comes the high purity regime, where the optimal decay rate decreases. So essentially, in the low and medium purity regime, the eigenvalues of the superoperators are complex. So in the sense that your approach to the steady state is is an oscillatory manner, and on the other hand, in the high purity regime, or in the optimal protocol for high purity regime, the eigenvalues of the superoperators are purely real. So the system approaches the target state in a fully relaxational dynamics. So the transition from the oscillatory dynamics to the relaxational dynamics happens through this medium to high purity regime via an exceptional point. This is the exceptional point of the superoperator, of the Lindbladian superoperator. Okay, so till now I have not discussed any noise in my protocol. So now I do want to discuss noise, but for that I want to go back to the simplest protocol where I don't have any local Hamiltonian. I just have an interaction Hamiltonian that couple my system with the detector. Okay, so what kind of noise I want to discuss? There are several kind of noise that we discuss in our paper. So the first is, what if the coupling parameter, this J, it fluctuates in time? What if this coupling parameter comes from a particular probability distribution? It can be continuous or static probability distribution, or it just have the coupling parameter might have a multiplicative white noise. So how do we go ahead with such kind of scenario? The second noise that I discuss is about environmentally induced perturbations. So what do I mean by this? Suppose I'm running my state engineering protocol, but there is some background Hamiltonian, some background noise that affects my system as well as my detector. So how does the protocol behaves in this particular kind of setting? So that the way we deal this kind of noise is just to add a stochastic Hamiltonian, which acts, or an arbitrary stochastic Hamiltonian that acts on the system and the detector all the time. And the coupling of that Hamiltonian is again a random number. And the third type of noise that we discuss is, what if you cannot prepare your detector, or what if you cannot reset your detector to the desired state after every measurement? Like you do a measurement, and then after the measurement step, you have to reset your detector to its original state. And what if due to some limitation, you cannot do that? So there is some error in the detector state initialization. And the fourth error is, what if you have a fluctuating steering direction? So what do I mean? That originally my protocol wants to go to the North Pole, but after every measurement step, there is some error. Like instead of going to the North Pole, it goes slightly here and there. And what if it happens after every measurement step? So these kind of errors we discuss in our paper in an analytical and a simulation perspective. So today I will not focus on all of these four errors. What I will focus on is this particular error where you have a fluctuating steering direction after every measurement step. So what do I mean by fluctuating steering direction? So suppose I have an initial state, which is denoted by the blue dot, and I have an ideal target state, which is denoted by the black dot. Now what happens is, like I switch on my protocol. So initially my protocol is supposed to go to the North Pole, but it decides to go towards this particular state, which is not the North Pole, it's the erroneous target state. After the first step, my protocol again fluctuates, and instead of going towards the ideal state again, it decides to go to some other randomly chosen target state. And this happens all the time. Like I can have the set of erroneous target state, could be any number. It goes from 1 to n. And there is an associated probability to each erroneous target state. Like with this much probability, my protocol will choose to go towards that erroneous target state after every measurement. And this just fluctuates. It's a completely random. So now I can write the stochastic Schrodinger equation for this particular scenario. Now I have two kinds of stochasticities in my problem. One comes from the measurement, which is the dn here, and another is another comes from the randomly chosen steering direction, which I call a chi. So how does it work? So for a given, although I have this n number of terms in my stochastic Schrodinger equation, because the I goes from 1 to n, but for a given time step, only one of those n terms are active. In other words, for a given time step, only one of the steering direction stochasticity is equal to 1, all other are 0, because at a given time step, my protocol is moving towards a fixed target state, and then it fluctuates. So yeah, so the mean of this steering direction stochasticity is given by this probability distribution, and this mean of the measurement induced stochasticity is bounded by the jump operator and the measurement coupling. Okay, so because I have two different stochasticity in my problem, so I can average them in many different ways. The first way is, suppose I don't average it, like I keep both the stochasticity. The second way is, what if I average only the steering directional stochasticity? And if I do that, I get a master equation, but the master equation is not the Lindblad equation, it's the stochastic master equation, because I do have a particular stochasticity sitting in my evolution. The third option is, what if I average the measurement induced stochasticity, but not the steering directional stochasticity? You can argue whether they are the physical scenarios or the imphysical scenarios. Essentially what it means, that averaging over the steering directional stochasticity essentially means that you have a fixed sequence of measurement outcomes. And with this fixed sequence of measurement outcomes, you average over the randomly chosen steering direction. And averaging over measurement induced stochasticity essentially means you have a fixed sequence of randomly chosen steering direction, and you average over click, no click measurements. And once you average over both the stochasticity, you do get this well-known Lindblad master equation, but there are n terms depending on the n possible steering direction that protocol can take. So if we have a stochasticity in our evolution, for example, if we have a partially averaged stochasticity, the stochastic master equation does not have any steady state because it goes and it fluctuates because of the stochasticity. On the other hand, if you average both the stochasticity, then this particular deterministic Lindblad equation, it does have a steady state. So here, for the simplest example, let's consider we have two possible steering direction, not n. So what I mean is, like, your protocol is allowed to go either towards this erroneous target state or towards this erroneous target state, but not to some other target state. So in that case, in our stochastic Schrodinger equation, we have this stochastic variable, which can be either 0 or 1, but there are only two terms. The first corresponding to steering towards this particular state, the second term corresponding to particular this erroneous target state, and only one of them is active for a given time step. Now, as I mentioned that we have different averaging hierarchies. So we study different averaging hierarchies for this particular example, and here the erroneous target states are parameterized by theta and phi, because I'm talking about the zx plane, so phi is 0 and theta is pi by 3. So these two erroneous target states are sitting symmetrically around the ideal target state with an angle pi by 3, and the probability going towards this one or this one in a particular time step is essentially equal. In principle, we provide a detailed analysis when the probability is not equal. It's some random, it's some arbitrary number p towards this direction and 1 minus p towards this direction. But for simplicity here, I assume they are equal. I can study such a dynamics, and this is how they look. So the upper panel is the Bloch sphere, and the lower panel is the zx plane of this Bloch sphere. So for the time being, you can ignore the upper panel and focus on the lower panel. So the first figure is essentially the case where you have both the stochasticities acting together. The stochasticity due to the measurement and the stochasticity due to the randomly chosen steering direction. So what do I see here? That whenever there is a jump occur in my measurement evolution, I go to one of the erroneous target state, and this jump I write here using the straight line. But if there is not a jump, then the system evolves deterministically, or the system evolves in a continuous manner along the arc of the Bloch sphere. So what does this mean? This means that when I have both the stochasticity in my evolution, and if I start from a pure state, I remain in a pure state. And remember, the ideal target state is the North Pole. Okay, so that's how it goes. Like you start from here, randomly you jump towards one of the erroneous target state, and then you evolve continuously. You either decide to go to that target state or this target state, but you always stay on the arc of the block sphere. In the second figure, I average over the steering direction stochasticity. So I have only the measurement induced stochasticity. And as I mentioned, that from the stochastic Schrodinger equation, which had both the stochasticities in the evolution, if you average one over them, you get a master equation, but this master equation is again stochastic. And because of the master equation, our jump is not towards the pure state, it's towards the mixed state. And after the jump, it again tries to go to the block sphere, to the arc, and then whenever there is a jump, it again falls back to this imaginary horizontal line that connects the two erroneous target state. So whenever there is a jump, my state will be on this particular horizontal line, but if there is not a jump, then it evolves continuously and it tries to go to the surface of the block sphere, depending on which stochastic direction appears. Then in the third plot, I average over the measurement induced stochasticity, but not the steering direction stochasticity. So here you see that your state becomes again a mixed state, and then this is this particular point and you wiggle around. But this particular point is in the upper half or in the upper cap of this block sphere. So another important thing is none of in these three cases where you have full stochasticity or either one of the stochasticity, you don't have a steady state essentially. But you are always confined in this upper cap. And you remember our ideal target state was the North Pole. What do I mean is like you always stays close to the ideal target state. You never come out of this cap. And in the fourth plot, I have the fully averaged dynamics. And the fully averaged dynamics does have a steady state. And this steady state lies very close to the ideal target state. Naively, one would assume that this steady state should lie on this horizontal line, but it is not. It lies way beyond the average of these two erroneous target state, and it lies very close to the ideal target state. And the fifth panel is just the ideal steering protocol. It happens when there is no particular noise. And we quantify errors using two quantifiers. The first is the fidelity. Fidelity essentially means we see how much our target state overlaps with the ideal target state. And another is the trace distance, essentially measure how far we are from the ideal target state. And I plot for all different kind of scenarios, when you have full stochasticity, when you have one of them, or when you average both of them, and when you have the ideal steering protocol. But instead of focusing on these figures, you can see here that when you have small errors, by small error I mean you are sitting here, you are sitting in the close vicinity of the ideal target state. Your ideal target state is the North Pole, and now it fluctuates by angle theta. And by small error, I mean the theta is very small. So if you have such kind of scenarios, then you can see that the fidelity is very much accurate up to the fourth power in this error. And this is very important. Why? Because if you just use projective measurement and the feedback, your fidelity drops by the second power. Like instead of theta raised to power 4, you will have theta raised to power 2. So our protocol in that sense provides a better robustness against just the projective measurement of the unitary evolution. And the trace distance is also up to the leading order, it goes like the error raised to power 4. So if you have a very small error, you get a very good robustness. So this is the particular case when I have the symmetrically distributed errors. This is the assumption I made. The another thing I chose is like there's a 50-50% probability to go either towards this erroneous target state or towards that erroneous target state. In principle, it does not have to be 50-50. It can be an arbitrary probability. And in our paper, we discussed this case of an arbitrary probability. Even then, the protocol carries a good amount of robustness. Okay, so with this, I come to the conclusion. And the first conclusion is typically people think that the measurement induced back action is a bad thing because it perturbs our system state. And what we show that it's actually not that bad thing. You can use this perturbation for a good purpose. And the good purpose is to manipulate your quantum state towards a desired target state. And the second thing is, if you decide to prepare quantum states using this particular protocol, so the protocol carries a good amount of robustness, which you don't get by simply measurement and the feedback. And the extension of these things can be done in many body dynamics, in the sense there was a paper from Stitadi and later by Cater. They prepare AKLT state using measurement induced dynamics. There also we can add this kind of errors and see how good the protocols are. And the another thing is, what about our target state is not a unique target state, it's a dark subspace or some kind of manifolds. And another thing, as Romito described in the last talk, some dissipative phase transitions. What if we have errors in those kind of protocols as well? All the, so whatever I talked can be found in this set of papers. And with this, I would like to thank for your attention.
Yeah. Thanks for the talk. So so you showed that for any point on the block sphere, there are 3 configurations that can lead to that steady state.
Yeah,
I was wondering if you considered using that as a resource against noise. So is it possible, for instance, to dynamically change the conditions between the 3? You know?
Yeah, very good question. So in principle, there are more than 3 ways to go. It depends on the set of parameters. But yeah, this is a nice possibility we have not discussed. We have not investigated this possibility of optimizing your protocol against errors using all possible set of parameters. Yeah. Okay.
Thank you for the talk. In practice, how do you fix the set of target states? Are there some rules or?
Theoretically, I don't fix it. Like I can choose. So here I talked about discrete set of target states, but in principle it can be in our paper we also discussed the continuously distributed target states. That there is some inherent probability distribution, which is, let's say, Gaussian or some other distribution, and with that probability distribution, your protocol fluctuates. So in principle, it could be a discrete or a continuous probability distribution, but how would you control it experimentally? I don't know. So maybe the experiment have some kind of systematic error that instead of going towards the desired direction, your protocol either go towards this or this. So same is the case when they apply the unitary feedback or pi/2 pulse or pi pulse. So it's not exactly a pi pulse or up to some accuracy. So it goes beyond pi. It's pi plus epsilon or pi minus epsilon. So something of that type.
And you have the same result of convergence? You have the same result of convergence with the other?
The continuously,
yeah. Okay. Thank you.
Okay, now we break for lunch, and the afternoon session will start at 2:30.